Hello, math application students, and welcome to your online lesson. Today we're going to be talking about Spearman's rank order correlation coefficient. If you haven't already been introduced to Pearson's correlation coefficient, you'd want to watch a video or lesson on that first. Our learning intentions for today is that we'll interpret and find Spearman's rank order correlation coefficient, and we'll also rank data such that the Spearman's rank order correlation coefficient can be applied. We'll know we're successful when we can use the Spearman's rank order correlation coefficient to solve IB level problems. So the first question is, what is Spearman's rank order correlation coefficient? So Spearman's rank order correlation coefficient compares two variables, an x and a y, by using their ranks to identify if there's an association between the rank of the two variables. And by ranking, we're talking about what you might be thinking of, like best to worst. So the best in one variable or one category or one way of looking at the data, is it also best in the other? And as we increase in our rankings or decrease, what happens to that other variable? Does it also decrease or does it increase, or is there no relationship that exists between the two variables based on rank? So these variables do not necessarily need to be quantitative, but they need to be what's known as ordinal, which is to say their values can be put in order or ranked from best to worst. So we could have something like maybe our favorite paint colors when we're selecting paint color to repaint a room or something like that. And so you could have your favorite ranked all the way down to your least favorite, and then maybe compare that with maybe the cost of it, where, you know, the least expensive might be the best in your opinion, and then the most expensive is the worst. So there we're comparing two things that aren't even, you know, both quantitative variables. One's totally categorical, you know, your favorite versus your least favorite, and then one is quantitative. And then you could also just have straight up quantitative continuous variables like speed, you know, the fastest, so the lowest time maybe that it took them to complete a race, or it could be a height or a weight or a score on a test or anything like that. Many types of variables can be ranked, but that's the important part. If they can't be ranked, then we can't use Spearman's rank correlation coefficient to analyze the data and see if there's a relationship between our two variables. We abbreviate the Spearman rank order correlation coefficient with a lowercase r, just like Pearson's correlation coefficient, but it has a subscript on it with the S standing for Spearman. So it's r sub s, and again, if we just see an r, lowercase r, we're assuming that's Pearson's correlation coefficient. We need to have that subscript r sub s in order to know that it's Spearman's. It's a continuous scale from -1 to 1, just like Pearson's correlation coefficient. And just like Pearson's correlation coefficient, we can have a positive association, which is, you know, values from 0 to 1, where as one variable's rank is higher, the rank would be higher with the other variable as well. Or we could have that negative, meaning as one goes up, the other goes down, comparing our two variables. As just mentioned, negative values on this correlation coefficient indicate in a negative association or correlation, meaning as one variable's rank gets higher, the other variable associated with this data piece ranks lower. And then positive values indicate that positive association or correlation. And then as we get r sub s values that are close to 1 or close to -1, that's a strong association, a strong relationship that exists. And then when we're close to 0, that's essentially no relationship or correlation that's existing here. If you go on the internet and look up scales for correlation coefficients, or even in textbooks, you're going to get a lot of different values as far as what people consider strong and what they consider moderate or weak or things like that. But a pretty safe way to interpret it is if our r sub s value is at least 0.85, greater than or equal to 0.85, that would indicate a strong monotonic relationship or correlation or association. You'll see all those different words sort of used synonymously describing Spearman's rank order correlation coefficient. But again, 0.85 and above for the absolute value of r sub s is definitely going to be considered strong on pretty much every scale. Some of them will go a little bit lower, maybe down to 0.8 or even 0.75 or 0.7, but you're really safe if you're thinking of strong as above 0.85. And then weak would be certainly anything below 0.5. And all other values, you know, in between that 0.85 and 0.5 should be considered some form of a moderate association. We mentioned the word monotonic here, strong monotonic, weak monotonic. What is monotonic talking all about? So monotonic data is when the size of one variable increases, so does the size of the other variable. So that's really what Spearman's test is, checking for. Spearman's rank correlation coefficient literally tests if the data is monotonic. It does not test if it's linear, like Pearson's. So what does that mean with some real world examples? Well, let's look at some graphed data here. This first set of data is perfectly linear. So on Pearson's correlation coefficient test, the R value would be like 1 or very, very close to it, because our best fit line would be super close or literally intersect all of the data points that we have here. And this would also be perfect correlation for Spearman's rank correlation coefficient. Our R sub S value would also be perfect, because as our X values go up, our Y values also go up. And then as we go over, it goes up, it goes up. So again, as our X is increasing, our Y is increasing, and that's true for every single value. So this is both linear, which would be a strong relationship for Pearson's, but it's also monotonic, which would be a strong relation for Spearman's. Let's look at another example. On this graph, we do not have linear data. This would not be nearly as strong on Pearson's test, because as we can see, the data starts off looking kind of linear. But, it's going from mildly increasing to much steeper increasing to very steep. This is really exponential data. And so it would be really challenging to draw a best fit line that would represent this data in any sort of linear fashion. We can see the data values are not particularly close to the best fit line that I just sketched there. However, this is still perfect data for Spearman's rank correlation coefficient, which is to say this data is entirely monotonic. Every X value, as we increase, the Y value increases too. At the beginning, it only increases just barely, hardly even noticeable that the Y is going up as we go from left to right on the X. But as we go further and further along, the Y value is now increasing by a lot, even though the X value is increasing by the same amount. The important thing is that as one is increasing, the other is increasing. And unlike Pearson's, we don't care about how big that gap is in between the values. It does not need to be a consistent ratio, meaning the same slope between each of these values. It just needs to have the X go up as the Y goes up and vice versa. Or if it was negative correlation, as the X goes up, the Y would be going down every time. Looking at just a couple other examples of monotonic data. This first example here in the top left, we can see that overall the data is increasing from left to right. So even though it's not perfect monotonic data, it definitely has a strong monotonic relationship. As we go from left to right, the data is increasing. So as our X increases, our Y variable also increases. And then you can see in the top right here, we have data that, once again, is monotonic and linear, but note that this would be negative monotonic data. As X is increasing, Y is decreasing, but it's consistently happening throughout the data. And the other thing to notice is that monotonic data, just like linear data, doesn't have to be perfect, and that's why we use that scale that goes from -1 to 1. So the closer we are to that perfect +1 or perfect -1, the more perfectly monotonic our data will be. And then at the end here, there's a couple examples of non-monotonic data that is not consistently increasing or decreasing. The one in the bottom right, it's increasing for a little bit, but then it switches directions, and so that would not be considered monotonic. All right, let's look at an actual example here to finish up this video. 8 student scores as percentages on their college entrance exam are given along with their unweighted grade point average in the following table. So 2 variables. One, their scores on their college entrance exam, and then their unweighted grade point average are given here. And so we can sort of look at this. We can find our student with the perfect GPA 4.0, and they had a pretty good score on their entrance exam, but there were some scores that were a little bit higher on the entrance exam. And if we use this data as is, we could find out how linear it is using Pearson's correlation coefficient. We'd use this data, list 1, list 2, like we've done on the calculator before. But what we're going to do is we're going to do Spearman's correlation coefficient. And in order to do that, we need to rank this data. Generally speaking, we'll rank it from best to worst. So number 1 is best, and 2 is slightly less good, and 3, and so on and so forth to the last value. They could be done in the other order. The important thing is being consistent, but I will go again from best to worst, where number 1 is best. So starting with the exam scores, looking at all of our different scores here, the very best entrance exam score seems to be this 92 that we had here. And so that's going to get a rank of 1. So again, I'm ranking these scores based on their value from best to worst. Our next best score is this 90. I'm just going to put a little mark there just to know that I've addressed that one already. So that's our second best score. Now we're down into the 80s, and it looks like we have 2 values in the 80s. We have an 85, which would be our third best score. And then we have an 82, which would be our fourth best score. Now we're into the 70s. I think we only have 1 value in the 70s, so that would be our fifth best score. And then we have a value in the 60s, which is our sixth best score. And then we have a value, 2 of them in the 50s. Remember, again, we're going from best to worst, so 57 is slightly better than 56, so that's our 7th best score. And then finally, our last score, the 8th student, ranked student, that is, had a score of 56. All right, we're going to do the same thing for the GPAs. Again, best would be the highest. So we'll start with this student who had the 4.0. We've got several scores in the 3s. So next best would be this 3.7. That would be our second best GPA. And then we've got a 3.5, which would be our third best. Now you'll notice we have 2 more scores, this 3.2 and then another 3.2 that are in the 3s. And they're a tie. So what we do with a tie, technically one of these would be like the 4th and one of these would be the 5th, but it wouldn't be fair to call one student 4th and the other one 5th because they're technically tied. They aren't going to both be 4th, though. What we're going to do is we're going to take these 2 values, 4 and 5, and we're going to find the mean of them, or average. Add them together. 4 plus 5 is 9, and divide by 2, because there's 2 scores here, which gives us an average or mean score of 4.5. So they're both going to get 4.5. So again, when you have a tie, it could even be a 3-way tie. Then you would average, if it was 4th, 5th, and 6th, you'd average those together, and they'd all get that value. So again, they both get 4.5 here because they were tied. And then since we had already, thought of the 4th rank and the 5th rank, we are now on to the 6th rank, which gets us to this student with 2.9. And then the 7th rank would be 2.3. And then finally our 8th rank, 2.0. All right, so now that we've ranked our data, we can actually find Spearman's rank correlation coefficient. So I've recreated that data that we just did there in this slightly more neat table. In order to find Spearman's rank correlation coefficient for this data, we're going to be using our TI-84 plus calculators or something similar. And so in order to get the data into the calculator, we're going to go with stat and then edit. Enter each data value, 6, 4, 2, 7, 1, 5, 8, 3, and make sure that, it's looking for the 9th value right now. We had 8 values total, so that looks good. And then going down our list for our GPA into list 2, we have 7, 1, 2, 6, 3, 4.5, 8, and then again 4.5. Make sure that your lists are of the same length. They need to have the same number of values, otherwise we'll get an error. And now we are going to calculate Spearman's rank correlation coefficient. To do this, we do it the exact same way as we do for Pearson's correlation coefficient. We go back to stat, but now we move over to calculate. So arrow once to the right, and then choice 4 on my calculator, linreg, line of regression, is what we're selecting. Make sure that your X data is list 1 or whatever list you put your data into. Our Y list is our other set of data. Here our GPA and L2. And everything else should be empty. No frequency list, no store, reg, EQ. Just arrow down to calculate or hit enter a bunch of times. And we are looking for that R value down here. And so our R value is 0.7904. Or to say that rounded to 3 significant figures, that would be 0.790. And so you might be asking, how do we know whether we're getting an R value, which would be Pearson's correlation coefficient, or an R sub S value? And it really just comes down to, did you put the original data in or did you put ranked data in? If you put ranked data into the calculator like we just did, then we're getting Spearman's rank correlation coefficient, or R sub S. If we put original unranked data in, then we are getting Pearson's correlation coefficient. Finally, we want to describe the relationship between our 2 variables, exam scores and the GPA. Since our R sub S value is positive, we know there is a positive relationship or correlation that's existing between these two variables. And then, we're not quite at 0.85. Some people might consider this to be strong data, so it would be positive strong correlation. Others might consider it more to be moderate. It's certainly in that border. IB, when they're grading their IB exams, understands that the scales can vary, and so they would accept either one of those interpretations. But I'm going to interpret this as a moderate positive monotonic relationship between exam score and GPA, which is to say, as our exam score increases, the rank of our exam scores, so does our GPA. Again, unlike Pearson's, this is not saying this is a linear relationship, but it is saying as one gets bigger overall, the other one does as well. In summary, a couple key aspects of Spearman's correlation rank coefficient. It works with nonlinear data, as we talked about. As long as you can rank the data, you can use Spearman's rank order correlation coefficient. Outliers don't have the same effect that they might with Pearson's. So if you have a really, really large value as your biggest value overall, it's still your highest rank. It's not going to affect the overall results like it would for linear data. We can use Spearman's rank order correlation coefficient without even having the original data as long as we know the ranks. And finally, you can change your original value data, and as long as it doesn't affect the ranks, as long as the second rank is still, even if its original score changes slightly, as long as it still has that same rank, it's going to have no effect on the R sub S value. All right, and that's our lesson for today. Till next time.